Uh, so we'll wait for 2 more minutes and then we'll start this. Uh, let's see if any other wants to join or not. Yeah, so we'll start this session. Welcome, good evening. Welcome to this electrical measurement and electronic instruments week 11 session. So I think we have 2 more sessions left for this. So maybe this Friday we may have this session for week 12, and then one last session in the coming week, Tuesday. But you will get the notification for this Friday session if that is going to happen. So we'll see. So by Friday we will complete all the assignment discussions and all. And the last week, the next week, we will be taking doubts, and I will be going through the, I think, most of the assignment questions, where like I will be again telling you how we solved some of the difficult questions, some of these difficult questions in assignments from week 1 to week 12. So we'll see that in next week. I think that is before your exams. So hopefully that will help you in revising all those assignment questions and the concepts again. But this week, week 11, this session, I will be going through the some these multivibrator equations, like these questions and the assignments, which and some previous assignment question which can help you solve these week 11 assignments. So let's start with the assignment questions of previous week, which are kind of similar, but they have this numerical differences, but the logic is same. So, so if we see the first question, yes. So they are saying, consider the above circuit of an astable multivibrator. So the first thing which we have is that this is an astable multivibrator using a 555 triple five timer. So we have these resistors which and this feedback loop of this with this transistor which is acting as a feedback, and we are getting a timer circuit. So you have seen this in lectures. So what they're asking is to calculate the peak to peak value of VC. So we have this VC here, and we have to calculate the peak value of this VC. So if you recall, if you recall your lecture, so what has been told, what I've been told. So we have this VCC, and based on that, this circuit will oscillate like this. Timer will oscillate like this, and the upper limit and the lower limit will be is given by 2 VCC by 3, and this is VCC by 3 if I am not wrong. Let me check first. I hope so. Yeah. So this is the typical waveform of a triple five timer, subject to the values of resistances which we have here. So you have to keep this thing in mind, that these resistors are equal. So we will be solving a question where these resistor values are different. So how we will be solving and how we will be getting the, so then in that case this will not be the upper threshold and lower threshold that we will be seeing in in this coming session. uh, but in this question, we have all these three equal resistors, 5 kilo, 5 kilo, 5 kilo ohms, and so we have this upper limit and lower threshold limit. So we can get VC, peak to peak. So if we talk about peak to peak, then it is upper threshold limit minus lower threshold limit. So we have 2 VCC by 3 minus VCC by 3. It is VCC by 3. So we have VCC is 15 here. So 15 by 3 equals to 5 volts. Okay. Uh, I think in your main exams, in your this final exam, this resistance values will be equal. But still, just be careful about like what is given in the question. Just don't blindly apply the formulas. Okay, you should know how those formulas are being derived. So how these limits are being derived. So you should know that. So that's why I would say there are some changes in the circuit, so you can solve that also. So this is quite straightforward from the lectures. So next question: when VC is increasing, then V out is. So let's see. When VC is increasing, so this VC, so this is increasing. What does that mean? So that means Uh, so this is a discharging path for this. That means this is not connected. That means this is not connected. So this transistor is off. So this is 0 or the logic here is 0. And it can happen when reset is 1. And when reset will be 1? When this is high. When this will be high? When this is high. So, and this is increasing, then V out is. So they are saying VC is increasing. That means this is the path which we are talking about. So this was off. So okay, V out. So okay, they only ask for V out. So V out will be low. So when V out will be low, then this transistor logic, then this transistor will be in reverse bias and it will not be operating as a like it will be an off switch. The switch will be off or the transistor will be off. That's why this path will not be there. And with this VCC voltage, we will be charging this capacitor. So ultimately, VC should be low in order to increase it. V out should be low in order to increase the VC voltage. So this is also quite logical. So even if you just remember the concept, you can answer this. Then moving to the next question, estimate the off time of V out. So the off time of V out, if we say, so you know that formula that T off is being derived in the sessions, and that is this C ln of 2 RA plus RB, I think. Yes. So this is T of time, straightforward. So if you know this value, so C is this, RA was I think this was RA, I think this was RB. Let me check first. Yeah. So this one was RA, this one was RB, and then we can get this formula. So 4 kilo plus 2.5 kilo into C is 0.25 milli into ln of 2. So you can get the answer easily in this. And just keep this thing in mind that sometimes this unit you will have to keep in mind. So sometimes they ask in milliseconds. So just be careful about that. Okay. So off time, if you want to go for on time, so next question is on time. So it is so if you remember for on C ln2, but I think only RA is there. Only because in on time this path is working. So this transistor is on and capacitor is discharging. So that's why in on time we will have only one resistor, that is RA. So yeah, RAC ln2. So RA is 4K 4K 2.5 milli ln of 2. So you will get T on. Now they're asking for the frequency of V out. So frequency indirectly means the time period of that output signal, and you know how output signal will look like. It will be looking like kind of this pulse waves, uh, oscillating pulse waves like this. So that will be the total time period plus T off will be the T total, and frequency will be 1 by T total. So if in terms of formula you can write this as C ln of 2 RA plus 2 RA plus RB. Okay. So otherwise you can add these two, like one from here and another from the, so T on and T off you can add, and then you can also develop, or you can get this question answer. So estimate the frequency. So yes, 2 RA plus RB, 1 plus CLR2. So this is also directly from the lectures formulas. So this seems simple if you know what was being derived in the sessions. But if somehow you forget these things in like your exams or somewhere, so you should know like how things were, how the flow of the circuit was. So maybe in case if if you're not able to remember these formulas, then what can you do? You can derive if you have time. If you have time, you can derive easily there itself. So you should know the basic logic, and then on the spot you can also derive. So it's not completely necessary to like required to remember all these formulas. Just know the concept how this thing is working, then you will get that. Now the next question. So this is a function generator that was being taught in the first session, first class of this week 11. First class of this week. Yes. So in this, there is an integrator here. So this is a kind of basic function generator, and then we have this Smith trigger, and this is a non-inverting Smith trigger. Easy way to get like when it, whether it is a non-inverting or inverting, like if the supply is at the non-inverting side, then it is a non-inverting Smith trigger. Okay, so this is the case. So the question is the waveform of V1 is, so V1 we have here, as you know, integrator, it will be integrating, but in this case what it will be integrating, it will be integrating this thing, this voltage which is being fed back from the output, and output is this V2. So, and what is V2? We know Smith trigger output is a pulse like this. So this is a square wave, and if we integrate that, we get a triangular wave like this. So basically, this integral will be having a triangular wave. Okay, very straightforward question. Then we have the next question. The waveform of V2 is, so I just told you the waveform will be square. This one. So even if you don't remember, like let's say they didn't mention whether this was function generator or not, so how you will get to know like what this is doing? So just look at this thing. So this is a positive feedback. Okay. So once a thing is in a positive feedback and its negative is like grounded or something, then you can get an idea or a feel like okay, this is a positive feedback. It's kind of an oscillating circuit, or we will be getting a saturation output from that. So this is important. Okay. So they may do that. There may be changes. This is not plus. This is negative, and this is plus. Then this completely changes this the output of this thing. Okay, that is simple and inverting this. So anyway, just be careful while reading the questions. Then the next one, the eighth question, estimate the peak to peak amplitude of V1. So V1, so peak to peak amplitude we need to know, and that will be this one. So again, it will be like that upper threshold minus lower threshold, and by that if we, so peak to peak, yeah, so it is something like this. So it is something, waveform, if we exactly draw something like this, V1, this is UTP, LTP. So V peak to peak will be UTP minus LTP. So this is V saturation or supply into R1 by R2 minus of minus V saturation by R1 by R2. Okay, I think this is the thing. Let me check. Let me check. Yeah, this is the thing. So we will have 2 times V saturation R1 by R2, and R1 and R2. So R1 is, I think, this one, R2 is this one. Okay. So accordingly you can, so then simply you can solve this. So it will be 2 into V saturation, we have this 12 volts, 12 into R1 is 4 and R2 is 6. It is 16. So peak to peak is 16 volts for this. Hmm. Then, so this is done, this is easy. Then the next question is, so estimate the time period of V1 in milliseconds. So V1, okay, time period. So time period, again we have this formula, that is 2RC UTP minus LTP. So it is good to like remember this formula in this form. Why, I will tell you. So what is happening, like this is the upper threshold point and lower threshold point. Okay. So there may be chance like in this mid trigger, what is, I will draw this circuit here, plus minus, there is a resistor here. So this is a, so indicator circuit is as it is, what we have seen in this is as it is, I have taken, and it is here. Okay, no issues. But what if there is some, let's say some feedback being given from here. So this was R1, this was R2, R3, R4. Then what this thing will do? So this is being feedback to this. So this will change the upper threshold or lower threshold limit of this. It's not necessary that this will be the case. There can be another circuits being attached to the negative feedback, or there can be something attached here like this, some resistor here. So the idea is, use the concept of finding the upper threshold or lower threshold of a Smith trigger, which you have read in week, I think, 10 or 9. So if you know how to solve for that upper threshold and lower threshold, then easily, even if you are like finding difficulty, if there is some complex circuit like this, then also you can use this formula and you can get the upper threshold and lower threshold points, and you can put that here and you can solve for the time period. So there may be changes in the circuit. Okay. So based on UTP and LTP, you can solve. So remember the concept of finding the upper threshold and lower threshold. So that is one thing. So but for this case, we have this the upper threshold and lower threshold was this V supply R1 by R2. So 2, it is 2 V saturation R1 by R2. We already have the saturation here. 2 RC T 2204 RC R1 by R2 T. So this is the case. Okay. So we have estimated the time period, we have estimated. So now estimate the time period of V2. So now in this case, this V2, which is this, so this is driving this circuit, and this is again driving back this circuit. So they have both have same time period. So we don't have to do anything special for it. So V1 and V2 are having same time period. T V1 equals to T V2. Okay. So this is also there. So we had, so this much was there for today's week. So okay. Okay, ninth question. Wait, wait. Estimate the peak to peak amplitude of V2. Which resistance can be adjusted to change the frequency of the generated signals without affecting their amplitudes? So in this V2, so you are saying which resistance can be adjusted to change the frequency of the. Acha, frequency is we have. So frequency is this one. R2, 4 RC, R1. Na? Let me check. Yeah. So this is this thing, and then to change the frequency of the generated signals without affecting their amplitudes. So you mean their amplitude means the amplitude of V1 or V2 now? So if we see, if we don't have to, so see whether anyway this is like in saturation mode. So this will be giving the saturation output. So even if we change this or this, it will change the frequency. But since this is being driven in the saturation mode, that's why it will always give either plus 12 or minus 12. So this its output will not depend on what is the value of its like feedback in this R1 or R2. So you can change either R1 or R2 for changing this changing the frequency, because if you change this is R, let's say, so what will happen then, you will be changing the this peak. Okay, so this peak is given by this was okay, we supply R1 by R2. Oh, okay. So this peak is basically we supply R1 by R2. Yeah, okay. So then don't change R1 and R2. You can change this R, because what is happening if we have this capacitor voltage which is being it's this upper threshold is given by V supply Vs R1 by R2 and minus Vs R1 by R2. So if you change these values 4K and 6K, then these points will change. But if you change R, then this will remain same. So you can adjust R but not R1 and R2. So I will write it down. To change frequency without affecting what's a voltage, UTP and LTP, change R, R1 and R2. Okay, not R1 and R2. Otherwise, by changing them, we will be changing the UTP and LTP of the integrator circuit. Is it fine? Are you still okay? So yeah, changing our will. Then so this was there. Any other doubts if you have? So for those who have just joined after some time, so this week I will be taking session on Friday also. There I will be completing week 12. I will be solving some of the previous year week 12 questions, week 12 assignment questions. Then we will be done with the lectures. But next week there will be again last session on Tuesday 6 to 8, and there I will be giving this. I will be going through all the assignment questions from week 1 to 12. We will be taking good questions from there, and we'll go through all the assignment questions one by one. Those which will be easy or something which I feel like they are fine, I will be skipping or I will be going fast from there. But for them, for the question which are like difficult, we'll be solving that in the week 12, the last week, yeah, the last session. That is next week Tuesday. But I hope this Friday also will happen session. That is week 2. Okay, so if you want to collect doubts for those weeks, for those sessions, then you can do that. It's not, yeah, yeah, we will be doing that. So okay, we are done with this. So I have some extra questions for this session, which will help you in like enhancing your concepts and giving you more insights about the question. So this is like from the op amps. So we have this circuit in the digital to analog converter. So this is from DAC, digital to analog converter circuit, shown in the figure below, where VR is 10 volts and we have R, that is 10 kilo ohms. Okay, the current I we have to calculate, that is this I, and we have to calculate V naught, that is this V naught. So just see how you can solve that. I'm giving you some time, so just go through it and try to solve. It's easy only. So just see this network. So try to find some symmetry in that and then try to solve that. So if you are going directly using models, then it will be difficult. But if you are able to find some symmetry and find some way to simplify this circuit, then you can solve this easily. Think in that way. So what we have, we here we have, see. So if we see this circuit which I have highlighted, this one here we'll see. So we have R, 2R, this is grounded. So this is virtual short, so this also kind of grounded. Okay, 2R, 2R, this is R, 2R. So if we see just this circuit, then so what is this? This is R. Again, oh shit, let me draw it again. So this is 2R, 2R, grounded, 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 grounded. R, 2R, this is VR, 2R, R, 2R. So this is the thing. So we can say these two are parallel because same voltage, and this is same potential. So we can say this is R, this thing. So this is R. So then this, by solving this, then this R is in series with this R. So this will be 2R. Then again this 2R, then we will have this circuit. This will be R now. So this we have solved. So we, this is grounded, 2R, R, 2R, R, 2R. So this again will be 2R, and 2R is in parallel with 2R, that will be R. Then again it will be in series with R, that will be 2R. Again parallel, R, then 2R, then R. And finally, we will be having something like this. This is VR, this is R rounded. Okay. Now again, so what was the current here? This was I in this branch. So this was I. So if these two are like having same resistances, then we can say here it was also I and here it was 2I. We can do that, okay, because this is having same resistances, so we can say the current is being distributed equally into each branch. So this is 2I. So if this is 2I, and we knew, and we also know from this simplification, this was 2R and this was also 2R. So means this equivalent resistance of this branch and this branch is same, that is 2R. So again we can say this is 2I, it was here 2I, so this will be total what, 4I coming into this branch. Then again similarly we can say that same thing for this branch. So this will be what, total coming inside is 16I. Okay. So sorry, 8I. 8I. So here also again that same logic, 8I and 8I. So it total from the input side it will be 16I. So now if you see again this thing from this side, so 16I I was coming, 8I went here, 8I went here, then 4I, 4I, 2I, 2I, and I, and what we were having, I here. So basically this is I, this is 2I, this is 2I, then this is 4I, this is 4I, this is 8I, 8I, and this is 16I. Fine. So we know that from VR 16I is coming. That means this is our equivalent circuit. 16I is coming. This is 0. So VR equals to 16I into R. And now what is VR? VR is 10 and R also we know. So this is 10 divided by 16 into 10K. We will get I. So I will be 10, 10 gone. So 1 by 16 is 1 by 16 is 1 by 16. You do that on your own. So this will be in milliamperes. Uh, you can solve. So this is the answer for the current. Now they are asking for voltage. Now for voltage, we solved for I and we know 16I is coming. Now we have to see how much current is going into this branch, because we know this is 0 volts. Okay. If this is 0 volts, then what will be V naught? V naught will be 0, and whatever current we know, let's say this is I2. So it will be minus I2R. Okay. So the voltage drop across this branch, that will be minus I2R, and this is V naught. And now the question is, what will be I2? So I2, see it carefully. I is coming from here, from this branch. So these two branches are connected. One this branch and another one is this branch. And how much current is coming from this branch? That is 4I. So 4I plus I, that will be total what? 5I. 5I will be coming here. So since this is an ideal op amp, no current is flowing through this. So we'll have 5I from the feedback of this op amp. So 5I goes into the feedback, and we have R here. So then we can substitute, this is 1 by 16 milli and this is 10K. So if you will solve this, you will get voltage out. Okay. So this is kind of a DAC, digital to analog converter. But how to solve that and all those things. So since you got this kind of symmetry between these two branches, again these two branches, these two, these two, and then you finally came up with an equivalent circuit, and then you were easily able to solve this. So this is it. Okay, so we have this. Now I gave you another question, this one. So this is a good question. So the question says that the circuit shown in figure is a 4-bit DAC. So we can give either 0 1 0 1 or whatever, 1 1 1 1 1, whatever you want. So digital we have inputting and we are getting analog output. So this is kind of a digital to analog converter. Now the question it says, what the question is saying is that input bit 0 and 1 are represented by 0 and 5 volts, okay, 5 volts respectively. The op amp is ideal, but all the resistances like these which are being used here, these, this, and the 5 volt inputs have a tolerance of plus minus 10%. Okay, so we see that there is a tolerance of plus minus 10%. The specification rounded to the nearest multiplier 5% for the tolerance of the diac. So they are asking for the overall tolerance of the diac. So when you, so this is basically percentage error calculation or proper measurement question, but at the same time you have to apply the concepts of op amp. So it's like a mixture of both. So how will be solving that in this case? So here if we see, so let's say, okay, this was 1111, something like that, and we have, so since this is a R and there will be no current flowing and there is no voltage source, so there is no voltage drop here, so this is also 0 volts. So we can expect 0 here also, that is virtual short. Okay, so this is 0 volts. Now we have one thing. Now the output, so we have to find the output of this op amp. So what will be the output? Output will be, so let's say this is V1 V2, we can say V1 V2 V3 V4. Hmm. That V1 V2 V3 V4 will be either 0 or 5 volts. That means 0 or 1 bits. So it will be V1 by R plus V2 by 2R. So if you just see V1 like this, then it is V1 by R, V3 by 4R, V4 by 8R into R, because we have this at the feedback. Let me check if this is right or not. You can also tell me if you have, if you have found the solution. It seems okay. So, and V1, V2, V3, V4, they can be either 0 or 5. So, let's for the tolerance, for the worst tolerance basically is worst case error. So, for that, we take this V1, V2, V3, V4 to be 5 volts, or we can say that is, yeah, that all are equal. So, that will be V by R plus V by 2R plus V by 4R plus, since we are going for the tolerance or the worst case error, that's why we need this that full potential. So now you may think, okay, we have this tolerance of these registers, we can add them and then we can solve them, but there is a catch, we have this plus signs in between, so we cannot directly use that division or multiplication formulas for error or tolerance measurement. What we'll have to do, we'll have to use the worst case for like how worst, like how maximum voltage V naught we can get from this. So how we will do that? So we had tolerance in only resistors, I think, yeah, or voltage also, but all the resistors in 5 volts. Okay, in inputs also we have a tolerance. So this was 5 volts. So plus, like, whichever thing is in numerator, we will take that as maximum value. So that will be 5 plus 5 percentage of 5, that will be 5.25. So this is the V max, and for the numerators we will be taking the minimum values of those just to maximize this V naught. Okay, that's how we will be calculating the tolerance of the overall dial. So R minimum will be, so R is, okay, so R will, so let's say R is R plus, sorry, minus, it will be minus r by 100 into oh, they have 10% of tolerance, sorry. So this is 10, this 0.5, 5.5 this is. Okay, this is 5.5. Then this will be r into 10. So this will be r minus zero point 0.1, that will be zero point 0.9. Okay. So if we substitute these values for getting V naught max, that will be, so we can take common, that is 5.5, and this is minus, by the way outside. So this is minus 5.5, 1 by what, zero point 0.9 plus 1 by 2 into zero point 0.9 plus 1 by 4 into zero point 0.9 plus 1 by 8 into zero point 0.9. Okay, and then we have this r here also, but for that r we will be using the maximum of that r, that is 1.1. So r max will be what, r plus r by 100 into 10, that will be 1.1 r, which is called like r. So this is the key thing. Okay, by solving this we will get minus 12.604 volts. So this is V max. Now, so the tolerance of the dancer. This is V max, and what we were supposed to get. So normal V naught would have been the normal values of all the voltages and the resistances. That is simple. 5, like taking common. 1 by R is what? R is R plus 1 by 2R plus 1 by 3R plus 1 by 4R into R. Simple. They are true values. So this come out to be 9.375 minus. So this come out to be this 9.375. So this is the true value of V naught true. The percentage error, or we can say tolerance, now it will be equals to, so 9.375 minus 12.604 divided by 9.375, that will come out to be 35%. This one. Okay. So when you were solving these multiplication and division tolerance questions, like to find the tolerance of worst case error, then you are simply adding those errors. Let's say there was this power question, like where you have to find that v square by r. So there is a tolerance of r. So you simply add that. So, but you cannot do that simply because we have this plus sign in between. So we have to maximize the numerator and minimize the denominator in order to get the maximum output which we can get from that system. And then we have to calculate the tolerance based on that. So basically, yeah, so this is the concept for finding this thing. So, yeah, so answer this next question, that is simple. An Astable multivibrator has. So now you have read this multivibrators and read oscillators in this session. So I think you can answer this. So quasi-stable means like it is like for some it's not stable throughout the time. It is like it is achieving some value, then coming, then changing. So so if I draw a waveform which is like this, okay. So this is like one quasi-stable state. So if you have like this, then this, like this. So you have one quasi second in one time period. You have two quasi states, then another one again two. Like it's getting stable for some time, but again it's changing its value. One stable state like if like it was there, you change something, it will be remaining like this. Or if you were like this, the signal was like this, if you change something, it will remain like this. That is one stable. Two stable states. Now this is a, how I say that, two stable states. So two stable states, like you only if we are giving a specific input, then only the output will change. It's not like voluntary they are doing. It's only if we give that. Like if it was there, it will remain there. Only if we give some input, then only, or if we give some specific input, then only it will change its state. So it's based on our will. We want to change that or not. But it can achieve both the states. Okay. So a stable multivibrator, since this is unstable, so it is having two quasi states. Okay. Either it so it like keeps on changing its state from one stage to another. So that you have seen in the waveforms also. So in the lectures, your waveforms for a stable multivibrator was this one. Yeah, this one only. Like the, you had this and the capacitor waveform was like this. Okay. So two quasi-stable states. Now moving to the next question. So just read that. Take uh, take some time, 1 or 2 minutes, and then answer this. I think it is clear only. So I will read the question for you. So there are two statements, basically statement 1 and 2. Examine these two statements carefully and select the answer using the codes given below. An astable multivibrator is also called a free running oscillator, statement 1. Then the second statement is an astable multivibrator circuit forces an operational amplifier to operate in the saturation region. So these are two statements. Now you have to tell, are these statements, first of all, are these two, both the statements, or one of them is true? Then which one of them is true? Second, is the first statement the correct explanation of the second statement? So these things you have to think for. Think. You don't have to solve anything. You have to just have to think. So if somebody is having some answer, they can chat. They can write in the chat box. So this astable multivibrator is like you know that it's like we just saw, it's two quasi-stable state. So it is an oscillator that we know because it is being operated in the positive feedback, as a positive feedback network, that we know. So that is an oscillator that we know. Free running, that is also true, like in a way it's true because it's like keep on oscillating, and it's like if we just give enough supply, then it will keep on running, like it will keep on changing its state like this and so on. So I think statement 1 is correct. What about statement 2? So statement 2 is saying an unstable multivibrator circuit forces an operational amplifier to operate in the saturation region. So the circuit which we make or which we use in a stable multivibrator, they are saying that it forces that operational amplifier which is being used in the circuit to operate that operation amplifier in saturation region. So I think this is also true. Why? Because this is what we are getting as output now. So this is a square wave, and this is V supply, and this is negative V supply. So all the positive feedback systems are running in this saturation mode. That's why they are being said positive feedback networks. They are not negative feedback. So this is also true. Now the next question: whether this first statement is the correct explanation for this or not. That is the that is the that is the point of thinking. As we know that it is a free running oscillator, that is fine, but so this is getting saturated because we have given a positive feedback. So this is a fact. This first statement is just a fact that okay, this is a free running oscillator, but it is not explaining or like explaining the statement too. That means like this op amp is in saturation region. Op amp is in saturation region. Why? Because it is in positive feedback, and that is not being clear from the first statement. They are not saying that it is a positive feedback system. That's why it is a free running oscillator, something like that. They haven't mentioned about this positive feedback thing. That's why we cannot say statement one is the correct explanation for statement two. So for this, we will be going with second option. That is statement 1 and 2 are individually true, but statement 2 is not the correct explanation of statement 1. Okay, so this was the explanation for this. Now this next question. So you have learned about IC triple white timers. So this is a question based on that. So they have used this IC. So whatever circuit you have seen that op amps and lots of resistors inside that, and that flip flop SR flip flop. So all are being there inside this, and you have this outer circuitry, and then you have they are saying that this is a typical pin connections with components shown in figure. For such application, however, it is desired to generate a square pulse. So they want to generate a square pulse of 10 kilohertz. Hmm. Evaluate RA and RB, and if the capacitor has the value of 0.01 microfarad. So this is, you know, configuration 2. If necessary, you can suggest modification in the external circuit configuration. So they are saying if necessary, you can suggest modification. So just to make this question simple. So since this was like a gate question from 1990s, so that's why this was a subjective question. So for that, but the logic here is that since they have told this thing, so we will consider RA equals to RB. That is one fact which we can assume. Since that there then in back then we used to have the subjective, so we can write R equals to RB. So then we can properly justify our answer. So, but anyway, RA equals to RB that we are taking. So if you know this, then you know frequency F equals to 10 hertz. Then how you will solve this? Think, think for 2 minutes. Then I will give you the answer. Just recall the circuit which you had in your lecture sessions, and how you will relate that to this, and those formulas to this formulas to this circuit. So we know this. What is total time period of an IC triple five timer? That is 2 RC. Sorry, no, no, 2C ln of 2. Sorry, there's no 2. I think 2 RA plus RB. Let me check once. Yes, CLN2. So we have this formula. So frequency will be what? 1 by C ln of 2 2 Ra plus Rb. Okay. If we know this, so 10 kilohertz we know 1 by point 1.01 micro, C value we know. 2, since we have used this condition, so this will be 3R and ln of 2. So if you solve this for R, you will get R and you will find the solution for this. Okay. Simple, like you just have to remember the, the total time which is being taken by this IC 555 timer. Now the next question. So it's again a 555 timer in the Astable multivibrator circuit. So 555 timer, but they have this Astable multivibrator circuit inside that. The frequency of oscillation at the output pin 3 is. Now they have mentioned their RA, RB, C. So again, I think this is straightforward. In this case, they have already given RA, RB, but they are asking this in another way. So frequency is what? Frequency is it was 1 by C ln of 2 RA plus RB. Okay, and one more thing to keep in mind. Let me first clarify that. So the resistor, so in your lectures, the resistor which is attached to the capacitor, that is, so in like theory, this is mentioned as RA. Just keep this thing in mind. The resistor which is attached to this capacitor, and the resistor away from this and being attached to the VCC, that is being mentioned as RB. So the formula which we have written here, that is, this RA is basically this thing 4.7. So I'll write this down here to 4.7. So it's kind of a confusion, but you should be clear about this. What my point? So the RA which was used there in your lectures, that is this RA which is being attached to the capacitor, and the one which is away from capacitor, that is RA. But here they have mentioned the other way around. So this also you have to keep in mind. The resistor which is attached to the capacitor, that is RA, and then only you can apply the formula that of that timer. So, yeah. So this variation may come in that your exams, your final exams. So if you know the formula, if you apply that wrongly, then that could be bad. So yeah, so this was this Austin material circuit question. Now the next question. Yeah, the only thing the it's like we supply is 9 volts here. Now you have to find the voltage VC across the capacitor varies between. Just first read the question. So the again there is a stable and a stable multivibrator circuit using IC 555 timer, and they are assuming that the circuit is oscillating steadily. So the voltage VC across the capacitor varies between. So VC we know how VC. So this is VC. If you recall, this is the voltage across the capacitor, and it is like capacitor is charging, then discharging, then charging, discharging like this, based on the transistor. So transistor is inside this IC. So based on that, this is happening, and you know what is the limit for that? That is 2 VCC by 3, and this is VCC minus. Sorry. Oh no, wait, let me check. What was the limit? So yeah, so this is not negative, I will say. 2 VCC by 3 and VCC by 3. Negative somewhere. Based on these values, so yeah. So this is 2 VCC by 3, VCC by 3. So if you, so we have the supply voltage, so it will be 2 into 9 by 3 and 9 by 3. So 3, 6, so 6 and 3, 3 and 6 volt. 3 to 6 volts. That will be the variation in the capacitor voltage. So this was also like if you know that concepts of that, you can apply directly. So you, for a stable multivibrator, you saw the questions where you didn't know about RARB. You assume you assume these values because they already told you want to take some, you want to do some modification. You can do in the external circuit. You did. You made this RA equal to RB. Then the next question. There you already know RARB, but you have to calculate the frequency. So this is second type. Third type is like. There is nothing mentioned about the frequency or the timing, but they are asking you about the upper and lower threshold limits of the capacitor voltage. Uh, so this also you saw. This is a question like related to your assignments also. Now moving to the next question. So this is based on monostable multivibrator. So we have this SR flip flop, also determine expression for. So they are asking for on time. So now remember in the starting of this session, I told you that in your lectures, these, and these registers are equal. That is R. But in this case, it is R by 2 and R. Okay. So now you cannot apply those formulas directly. One thing, and for coming to that point, you should read the diagram or the question properly, then only you will be able to know that. Otherwise you will simply apply that and then it will be able done. So once you get to know that okay, this is not that straightforward question, you will have to derive the formulas for that, like then you have to apply the basic concept of how you derive the formulas for that R and like 3 R's, that formulas for that monostable multivibrator in your lectures. So they are asking for T on, we'll go for T on and T off. Okay. Hmm. So we know this one. Let me first open that waveform that I don't commit any mistake. So was yeah. So now in this case, let's see. So what will be this voltage? So this is like so we have to calculate this voltage and this voltage. So so this is ground. This one is ground. Okay. So this will be VCC by I will write it here. Yeah. So this voltage will be what? VCC into R divided by the total resistance. So total resistance will be R plus R by 2. One thing. And what will be the resistance? What will the voltage for this? It will be VCC into R plus R by 2 divided by the total resistance of the branch R plus R by 2. So we have VCC 2R plus this is 3R divided by 5R. 2R will cancel it. So it will be VCC 3 VCC by 5, and this voltage will be VCC by 5, 2 VCC by 5. So we have two things. So our voltage should be doing like this. So the upper limit is 3 VCC by 5 and lower limit is 2 VCC by 5. Okay, so then again, till what value it would have been, it would have gone, like what you have seen in the lecture. So till what final value it would have gone if this oscillations would not have been there. So that would be VCCC, that basically the supply VCC. Okay, but it's not able to achieve that value. So if we talk about this, so this is T off, this is T on, same thing what you did in the lectures. So if we calculate T off, then it will be just this way. So T off will be this. So initial voltage is what? So that will be 20 off. So VCC V final minus V final minus V initial, that is the capacitor voltage equation. So E minus T by tau, and tau in this case is in that you saw R, this RA plus RB, that same RA plus RB will be there, and it will be C plus. Okay, so but anyway, that RARB is not required that much here, because we have to find just the expression. So this, since this is also a gate question from 90s, so but if like if there is some modification, if you get the question in this this final exam, then definitely you will be given this RARB these values and all. Yes. So whatever. So we have this RA plus BC. So V final is what? V final would have been VCC. VCC minus V initial is what? 3 VCC by 5. E to y minus T by L. And just for the timing, I'm saying tau. So this is 3 VCC by 5. So if you solve this, you will get ln 3 by 2 RA plus RB into C equals to T off. Now what will be T on? So for this period, so final value what? It would have been 0. Again that same concept. So final would have been 0. So initial what is the current value? That is 2 VCC by 5. 0 minus 0 minus 2 VCC by 5. Initial value, final value, and this is our final E2 by minus T by. So here tau is different, so I will say T tau. But if you solve this, so this is what this T is, T on. So if you solve this equation, it's simple, then you will get ln 3 by 2 R A. So this is the resistance which is being attached to the capacitor, R A into C. So we have T off expression, we have T on expression. So the things which remain same, those are this thing, RAC, and this CRA plus RB. So uh, you can remember like this also. Okay, this will remain constant, but this factor ln, it will change. So for this you have to be careful. So this will be changing. Earlier it was ln of 2, but here it is ln 3 by 2. And if we may find some logic behind that, then let me see. But yeah, it depends on the figure 5. Actually, it depends on the ratio of threshold voltages. So I'm just giving a guess. So this was this. So what was UTP by MTP now? So if we let's check. So UTP is this one, 3 VCC by 5. So this will be 3 VCC by 5, and into LTP is this one, 2 VCC by 5. So VC by 5 cancelled, ln 3 by 2, and that is what the ratio which we are getting, ln 3 by 2. Okay, just to be sure. So what was the voltage limits, voltage upper thresholds and lower thresholds in that earlier case, which you have been told in the lectures? That was 2 VCC by 5 and VCC by 5. Yeah, it's making sense. So this is what? So ln of 2 upper threshold, so 2 VCC by 5 into VCC by 5 by 5 VCC. So this is ln of 2. So earlier when what you studied in that lecture, so that was ln 2. So now if even if like these resistors are being changed, so just get the values of the upper threshold and lower threshold, and you can derive the, so T on and T off you can derive easily without solving this much. So where should I write? I will add a page here. Wait. Yeah. So T on equal to, so this will be RA will be there. So RA is the capacitor which is attached, sorry, resistor which is attached to the capacitor. RAC into ln of UTP divided by LTP, and T off is RA plus RB into C ln UTP divided by LTP. So this will keep in mind for these questions. Okay. For this particular type of question, if there is variation in this or sorry. So if there is a variation in any other part, then you will have to derive it. So the best way is to know the basics of fundamentals. That's the best way to solve it. Otherwise, you always have some formulas which you can defend. So this was this question. So yeah, moving to the next question. So now some oscilloscopes, since it was being taught to you these oscilloscopes. So see this question, read this, just try to think and answer. I don't know whether this concept is being taught to you. I'll give you a formula for this. If not this, then this can help you in gate. So anyway, it will be useful. So if you have not been taught about this, so just it's simple. Like whatever pattern, like so here it is. They are saying 8. Where is this? Display of 8 is there on the oscilloscope. Okay. So just this kind of a shortcut. Uh, so so basically this Fy by Fx, yeah, that is the frequency, the ratio of these two frequencies Fy by Fx, two signals like the y channel signal and x channel signal. The ratio of them is given by number of horizontal tangents divided by number of vertical tangents, and I will say these are maximum maximum number of horizontal. What does that mean? So don't worry, so this is a pattern, so just cut this pattern horizontally. So if you cut that horizontally, then it will be what? This. And you have to make sure you are cutting this for the maximum number of times. You cannot cut from here, it is only one then. Okay, so that's why I said maximum. So maximum you can cut this horizontally for two number of times. So this will be 2 divided by the number of vertical tangents. So maximum number of vertical tangents with like cuts you can make. So you cannot make from the middle, otherwise it only be 3. You can do like this. So this is 1, 2, 3, 4. So 4 cuts you can make by fully. So this is 2 by 4. This is 1 by 2. So now you have the X signal frequency, that is 4. Okay, so that is 4, and Fy you have to calculate. So Fy will be 4 by 2 is 2. So only one option is there which is saying that 2 is there in that frequency type. So this will be the answer. So we these are not the answer. 4, 4, 4, 8, 4. So instead of 8, if this was making a circle, then this is horizontal maximum can be 2, vertical maximum can be 2. So 2 by 2 that will be 1. So the x signal frequency will be equal to the y signal frequency, and then it would have been either of this or this. Then they would have given more data in the question to solve for this phase or something. Okay. So this is like, I don't know if they have if you have been taught this concept or not. But anyway, it will be helpful for your gate exam. So yeah, this. So if you you can read. I think it's clear, but it's little small. So I will read it for you. So list one represents. So these are the represents. These are the angles. Represent the figures obtained on the CRO screen when the voltage signal Vx equals to Vx sin omega t, and Vy is Vy at sin omega t plus phi. So there is a phi angle difference, angle of phi. I've given to its x and y plates respectively, and phi is changed. So X and Y plates of the oscilloscope, they have given these two signals, and this phi they are changing from P to Q, then R, then S. Then they are saying what will be the change in pattern. This we say Lissajous pattern. Okay, so what will be the change in the pattern? So I will write down this table for you that you can remember. So phi equals to 0, phi equals to, or phi it is greater than 0 and less than 90, phi equals to 90, then we have phi equals to, sorry, greater than 90, less than 270, sorry, 180, then we have phi equals to 80. So I will tell you what are the messages patterns which you get for different angles, different phase difference. So phi equals to 180, then phi equals to 270, then phi, this is 270 and 360, then phi equals to 360. Okay. So for phi equals to 0, it is like a line. So if there is no phase difference between the x and y signals, then the line is like this. Okay. If there is some difference between 0 to 90, that phase difference, then it becomes like this. If phi equals to 90, then it becomes a proper circle. Hmm. Then 90 to 180, then it will tilt like this. Okay. Uh, no, no, no. For this, it will be like this. Okay. For I think there's some. I think it will not be like this. Okay, for the time being, but I will just correct this in the next session. I forgot. But anyway, for phi equals to 180, it will be like this. Then again for 270, it will be this circular. Then 270 to 360, it will be like this. And then we have back to 360. I'll check for this. Uh, the next session I will check for this. So based on that, you can answer this. So we have one. So A equals to, so A is what? A, I think that is A, B, C, D. Okay, these are A, B, C, D. So for phi equals to 0, that will be 1. So we have these two options. Then for pi by 2, so 90, we have 3 or 5.
5 is to 90. 5 is to 90. We have a circle. So the nearest to circle is this. So I think D is the answer for this. But anyway, I will clarify this now. Yeah, so D will be the answer for this. Okay, so this was about Sage's patterns of oscilloscope. Then we have one this question. So this is saying that X and Y sensitivities of an analog oscilloscope are set as 2 milliseconds per centimeter. So for X it is this, and Y it is this. Respectively, the trigger is set at 0 volts, okay, with negative slope, and input of 2 cos volt like this much is fed to the Y input of the oscilloscope. So this is the Y input channel. The waveform seen on the oscilloscope will be, so we have a signal of 2 volts minus 2 volts and a frequency of 100 pi by 2 pi. So this is 100 pi t, so that is omega. Frequency will be 100 pi by 2 pi. It will be 50 hertz. Okay, so this is 50 hertz. Now amplitude, first we go. So this is for all of this. So this is y, and this is x. So we have 2 milliseconds per centimeter. So we know that our peak to peak is what, 4 volts. So we, based on this based on this y, that is the amplitude, it will be how much? 4 volts per cent. So 4 volts for total cent, like for so that will be 4 volts in total. So 1 centimeter requires 1 volt. That means it will be requiring 4 centimeters for 4 volts. That means we need 4 blocks for this. So let's see in which diagram we have 4 blocks on the y-axis where the circuit is being covered. This signal is being covered. So this, let's say this is the peak here and this is the peak. 1, 2, 3, 4. We have 4 blocks here. In this 1, 2, 3, 4. Again 4 blocks, 4 blocks. 1, 2, 3, 4. 4 blocks. 1, 2, 3. So we have 4 blocks. So now the difference will be created from the x-axis. So let's see what x-axis says. So we have f equals to 50 hertz. So the time period will be 1 by 50. That will be 0.2 by 10, 0.02. That is around 20 milliseconds. Now we have 2 milliseconds for 1 centimeter. Okay, so 2 milliseconds for 1 centimeter. For 20 milliseconds, how much blocks it will take? 2 into 20, that is 10 blocks, 10 centimeter. So we need 10 centimeters. So basically the signal will be 1, 2, 3, 4, 5, 6, 7, 9. So all are having this 10 centimeter block, but we may have some differentiation. The waveform seen on the by t plus 30. Trigger set at 0 volt negative slope. Okay, so since the trigger is at negative slope, the side, the waveform will be, so one more thing, the signal will be completing one complete cycle for this 10 blocks, because this we are calculating this full one time period for that block. So so definitely this cannot be the answer, okay, because here we have two cycles. That is one thing. Another thing, now the so this one is like this also complete cycle, this is also complete, and this is also there. Now we have to see, so we have 30 degree of phase shift also. Okay, but okay, now we have these two things. First of all, the trigger is set at 0 volts. That means it will start this signal from 0 volts. The signal will be starting from 0 volts. First thing. Second thing, it is having negative slope. So what will it do? It will make the signal to start from its negative cycle. So trigger set at 0 volt. That means whatever signal was coming, it will show from the zero, first thing. And second thing, since it's negative slope, so that it will start from its negative cycle. So we will get this. Okay, here no 0 volt starting. Here it is 0 volts, but 2 cycles. So no, this is not. So this is starting from not. This is not starting from 0 volts. So no, only this signal is starting from 0 volts, and it is inverted like from its negative cycle. So this will be the answer. Okay. So this was the answer for this. So if you need some clarity, you can ask me again. No, then we can move. So you have to keep in mind when the trigger is being set and what is the slope for that trigger, and you can answer that. So now I think this is the last question and what and nice and good question. So I will give you some time to read this. So I think you all know Laplace. That is being told to you I think in second semester or third semester. So yeah, so this is the question. So there are probes of non-isolated two-channel oscilloscope. So there was one oscilloscope. So probes were being connected from this. Okay. This. Clip to points A, B, and C in the circuit of the adjacent figure. So this is the figure. Vn is a square wave of a suitable low frequency. So this is a low frequency square wave. The display on CH1 and CH2. So channel 1 and channel 2 is being given by this. Then the signal ground probes, that is S1 G1. So there is this also you have seen. So there are these signals. So one is S1, G1, S2, and this is G2. So one probe you are attaching to some part of the circuit. Another this, so this is channel 1, this is channel 2. Okay. So this channel you are attaching to some part of the circuit, and this channel 2 you are attaching to some part of the circuit. So now you have to say what like at which point which probe is being connected. So that you have to see. Just think how you will approach this. Then I will tell you the answer. Just think. Take some time. So they have given that this is ground. That means this is 0 volts line for that oscilloscope. Think. I'm drawing the circuit. Right? So we have a square pulse input V in of low frequency R, and this is L. Okay. So the first thing we have to see. So this is basically the voltage which is being dropped across R and L. So we have to find the voltage equations across R and L, and then we can comment then we can comment on the probes. So how we will do? Let's say we will find the expression for I of t. So what is I of t? So V in minus I of t R minus L di of t by dt equals to 0. You know this, okay? This is a differential first order differential equation because we have an inductor in the circuit. If we convert this into this Laplace domain, so what will happen? So this is a square. pulse, and for a square pulse the Laplace transform is will be the amplitude of that pulse, let's say a divided by the s e to the power s by t minus 1 e to the power, sorry, st by, this was st by 2 st by 2 minus 1 plus 1. Okay, so we have to use this fact that it is a very low frequency signal. So if this signal is low frequency signal, that means frequency is almost zero. So t is almost infinite. So if t is infinite, then this thing will be what? If we calculate the limit of this thing, then it will be 1. Okay. So v in Laplace will be equal to a by s into 1. So it is basically a by s. So using this thing in this equation, you know the Laplace of this. This is ls, simple. So a by s minus capital I am writing r minus ls equals to 0. So I is also there. So if you solve for I will be a by r 1 by s minus 1 by s plus r by l. I've just rearranged the terms here and there, and then I came across this. So I of t will be, I will just write v in only instead of a. V in, you can say it's the amplitude. So this will be 1 minus, so this is e to the power minus r by l t. Okay, r by l t. Now we will first calculate. So this was the circuit. Now we have the Laplace. Now we have the time domain equation for this circuit. So this was A, this was B, this was C. So we have I of t expression with us. Now this oscilloscope is reading the voltage across these two elements R and L. So let's say what will be VAB, that is the voltage across drop across this R. So it will be I of t into R, simple. So that will be V in R by R will cancel, it will be 1 minus e to the minus RT by L. So if you draw the waveform of this, then it will look like something like this, like the first this one. So for this it will be 0 and this. Okay, so this is V, this is T. So this you already know, simple maths. Now, so this was VAB. Now what will be what will be the voltage drop across the L inductor? That is VBC. It will be VBC equals to L d I of t by dt. So we will have to differentiate the I of t expression. So it will be V in by R L minus r by L e to the power minus rt by L. So minus, and so this, there was already this minus here, and minus minus it will be plus. R will cancel. V in e to the power minus rt by L will be the expression. So now if you draw the waveform of this one, so it is like so it is like something like this. So even if you don't know like how, so just go for t equals to 0. What will be t equals to 0? So it will be v in something, v in, it will be starting from v in. T equals to infinity, so this is t infinity, it will be what? It will become 0, so it will be going towards 0, simple. So that you get a raw waveform of this. But instead of this, what we are getting at the oscilloscope, we are getting, so this was ground, so we are getting an inverted, a mirror image of that in that circuit. So instead of this we are having what? So this was the ground reference voltage, so we are having something like this, that is channel 2. So this is channel 2. Okay, now these are the observations. So this was channel 1. So channel 1, we are getting what we are getting VAB voltage, that we are getting like this. And in channel 1 in the oscilloscope also we are getting the same signal or same shape of waveform in the channel 1. That means VAB voltage which we have calculated, that is for that the probes are, so for A, for this point, A is the signal S1 and B is the ground G1. Because we calculated VB and we are getting the same signal which we are getting at the oscilloscope. So that means A is at S1 and B is at ground. Simply we have connected this, and that what we are getting at the oscilloscope output, channel 1. For channel 2, we were supposed to get this. Okay, this is VBC, but we are getting this, the lower volt, this one. And how we can get that? If we reverse the B and C polarity of the oscilloscope. So this is what? This is VCB. This the mirror of that. So if this is VCB, that means C is connected to this S2, that is the signal input of the oscilloscope channel 2, and B is connected to the ground 2 of that oscilloscope channel 2. So B, so this B for channel 2, so this is for channel 1. For channel 2, B is at G2, and so it has been inverted. C is at S2. So now, so we have to find S1 G1. So S1 is A, G1 is B, S2 is what? C. So S2 is C, G2 is what? B. So this is what the A, B, C, B. Yeah, this one will be the answer. Okay. So we saw that, so we connected these oscilloscope channels to A, B, C. We didn't know where these are connected. When we found the expression, voltage expression for this resistance and inductor by using Laplace and getting back the time domain equation for the current, and then we found the voltage. Then we came to know for resistance, whatever we were getting as a drop across its voltage, that same thing we are getting as the output in the oscilloscope. But for the inductor, we were supposed to get this, but instead we are getting a mirror image across this x-axis, and that is, instead of VBC, we are getting VCB. So that means like the oscilloscope channels are being inverted across the inductor, and the signal is being connected to C, and the ground of channel 2 is being connected to B for inductor. So that's why we are getting voltage like signal form like signal form like this. Okay, so this was all about today's session. So if you have any doubts, you can ask me. Otherwise, we'll meet maybe Friday, let's see, and next week also. So thank you. So if you don't have any doubts, then you can leave the session. If you have, you can like chat. You can write in the chat box. If no, then I will end the session now. I'll end the call then. Anyway, you can ask me in the discussion forum or like in the next class also. Thank you. Welcome back. Yeah. So I will end the call.